So, this video is for the people who are trying to do the forces activity. Uh, I had a fair, and so, as you can see here, I have the actual application open, and off over here that I have the PDF open so we can go through it. All right. So, you saw what uh, the app looks like, right? And note on here that there's a blue arrow that is the force of gravity, and there's these things here that they're not obviously controls, but that's what they are. You can click on them and turn these arrows on and off, and then you can control these settings up here. All right, and so we ask you to go through and do certain things, and in particular, um, you know, asked you to try to set the settings uh, equivalent on the on the friction coefficients and the mass as I'm doing here. It doesn't come out exact. Um, get as close as you can on it, um, but you want to make sure that uh, you actually do it. That's the sort of the thing. All right, and so as we go through, you're going to go through. There's going to be these arrows, and you can change the arrow. And so I'm going to click to change this angle, and you see that it rises up. And we're going to let it run. And now, right about here's a good stopping point. You can see that the force of gravity, I can turn it on and off. And then I can turn on and off the normal force, and I can turn on and off the friction force arrow. This is the free body diagram for this object. It doesn't have the labels on it, but the blue arrow is the weight force, and then the red is the normal force, and the green is the friction force. Right. So the weight force is just the mass times g. It is fixed, and so you can take and multiply these numbers out and get what that weight force is. Right. It's going to be 9.8. Right. These are unusual units, newtons per kilogram. That is the units for acceleration. It's meters per second squared. Right. If you go in and break down what a newton is, that's what you'll recover. And so you would take 0.7 kilograms times 9.8 newtons per kilogram, and you get about 7 newtons. Which direction is a point? It's straight down. All right. And then with the incline level, that's going back to this picture up here, there's only two forces on it. If it's not moving, the system is balanced. These forces have to be the same size in opposite directions. So you would get the same force, and it would point straight up. So we set up at some angle, in this case about 15 degrees, and I ask you, did the weight force change? Can you tell a difference between this weight force and the others? Or in particular, what would have changed the situation? Did you change the mass of the object? No. Did you change the Earth? No. Then the weight force should be the same. But the normal force, you have to measure it. All right, and if I measured it off of this, the way it's set up, each one of these divisions is a newton. This is about 8 newtons. No, about 7 newtons, sorry. I can't count. All right, 10 is up here, and it's between 5 and 10, and you can see that's about 7. And then the friction force is about 2 newtons. And then note, they are not straight up and down or straight horizontal. They are along these rotated X and Y axes. They are perpendicular to the surface and parallel to the surface. Right. And so if you're careful, you could draw these arrows out, and you can confirm, all right, basically you take this friction force and move it down to the end of the weight force, and you move the normal force to the end of the friction force, and they should add up to 0. So you be very careful. Here, what you would do is split the weight force into components, and you would see that the x component of the weight force equals the friction force, and the y component of the friction force, of the weight force equals the normal force. So, in the rest of the lab, we want you to make the block start moving and figure out when does it slip. You may have to do this a couple of times. All right. So we're going to let it go. All right. So we're going to start again. But you saw it was about 27.5. So we're going to let it go again. All right. So you saw when it just slipped. And the idea is you know that angle. The question is, does it line up with calculating what that critical angle would be? And so the idea is, if you know the components of this weight force, you know what the friction force needs to be. But you know that if it's just about to slip, then this friction force has to be mu times the normal force. And so you know what those are, right? So you can estimate it based on these. The friction force will be about 3 newtons, and the normal force will be about 6 newtons. And that is about 0.5. So it's pretty good. All right. 0.5 times 6 newtons is about 3 newtons. So it's pretty accurate in that sense. But can you calculate this critical angle? And that means comparing the friction force to the x component of the weight force and the normal force to the y component of the weight force. And right, that coefficient of friction is the ratio of the friction force to the normal force, which means it's a ratio of sine theta to cosine theta. Right? I'll have to draw that out for you here in another video on paper. But that coefficient of friction is a ratio of sine to cosine, which means it's tangent. So mu should be tangent theta. And if you calculate tangent, all right, let's just do that, 27.5. And we calculate tangent of that in degrees, you get 0.52. That checks out. So if you've done the lab carefully through these steps, that's what you should see, is that it works out. All right, so for the second part, friction between materials, we're going to open this app up, and we're going to begin. And this is something we will do in the lab. I'm not really concerned if you get this 100% correct. But the idea is you're going to try to pull this block across this table. And what you're going to see is how much force you can add to it before it starts to move. And so you see this peak value is the friction force when it's just about to move. That lets you get that static coefficient of friction. And then you have this range, which is when it's moving. All right, let's show that. If I, let's see, what mass do I need to set it to? Does it say, or set it to a range of mass? All right. So let's drop it down to 100 like in the first picture. So we hit start. The force goes up. And it slides. All right. And so there's the graph. Let's reset it and do it again. All right, so looking at this graph, you see it go up and then it slips. And once it slips, it's a constant force, no matter how it's, no matter what it's accelerating as, you're applying a constant force. And that's that friction force. Right? So you can see right there is where your friction force switches from static to kinetic friction. All right, so you can find this value. It's about 0.11, and this value is about 0.075. Right. So you can look at those values, and you can look at the situation. It's a block sitting on a table. So you would draw a free body diagram for this. There would be a normal force, a weight force, and a friction force, and a tension force. And you're measuring that tension force. So you're measuring, in effect, the friction force as it starts to go up. And then you're measuring as you pull it across the table. You're measuring the tension in the rope. And if you pull at constant velocity, the forces are still equal. That's the key thing. If you pull at constant velocity, then you can calculate from these formulas what these coefficients should be. Right? And so the idea is this part of the lab will let you get to what you would do in the lab with actual materials. But you can relate the friction force, which you're getting from these measurements, to the normal force, which you can calculate from the object's mass, which you play with. You can adjust it up and down. Oops, I'm on the wrong thing. You can reset it, and you can adjust the object's mass up and down and get new data. And you see that it, you get a higher force in both cases, in both when it's static and when it's moving. But if you calculate the coefficient of friction, it should come out equal. And so do your best with this, but don't worry too much about completing it. I can go over your questions when we're back together in class again. Just do your best with it. Be patient. Don't worry about it. You are going to get a chance to do hands-on in the lab.